Hi everyone. In this video, I will show how to create deployable versions of PyTorch pretrained ResNet50 model. The final goal is to deploy ResNet50 model on AWS Sagemaker using Nvidia Triton inference server. So in this video, I will concentrate on the task of creating deployable files. So we start off landing AWS GitHub repository, and we will find Amazon SageMaker examples section here. Then we will scroll down to SageMaker Triton. And in this folder, we will go to ResNet50 folder. And here we need workspace. So workspace folder contains 3 files. So the first file is generate models.sh. This is a bash script file. We will talk later about the content of this file. But at first we will consider ONNX _exported.py and pt _exported.py. So the first file is a Python script which allows to convert pre-trained ResNet50 model, which is contained inside PyTorch library, into ONNX format model. And the second script allows to convert the same ResNet50 model from PyTorch into the TorchScript module, script module, which can be deployed later. So let's start off investigating the files and let's see what they look like. So we will start off ONNX _exported.py, and first 4 lines, these are inputs. Here we import PyTorch library itself, Torch Vision library with models, so we are particularly interested in the models. Then we import argparse, which is a parser of the line command arguments. And finally, we import OS module. Then in line 6, we make sure that this script is running as a standalone application and is not called by some other Python modules. So lines 7, 8, and 9 are dedicated to creating a parser. So here we define the parser itself in line 7 when they set a default argument, when they set argument save and provide default value for that. Model.onnx. This will be the name of the ONNX deployable file. And then finally we create the parser itself as variable args. Next, we download ResNet50 from model zoo, PyTorch model zoo of pre-trained models. And then we create a dummy variable of the size 1, 3, 20 to 24 to 24. So this will be the torch tensor with random values. This is needed to provide a system or to provide the exporting tool with the dimensions of the input. And then finally, we convert ResNet model into inference mode. So the eval method of the models in PyTorch, it implements reduction of the layers which should not be used during the inference. Examples of such layers are, for example, batch normalization or dropout layers, and so on. Finally, we call torch ONNX export method, which is taking model itself as the argument. So this is already model optimized for inference. The dummy input, so we need the dimensions, the name of the file to save, then we say that we want to export parameters. This is the offset version. And do we use a constant folding or not? And then these two parameters are very important input name and output name. So these two will be crucial. Then we deploy the model using the Triton server, because these are the names we will have to provide for the model input and model output names. And then finally, we provide here the batch size of output and input. So after calling this method, if everything's okay, script will print out message saved. In this case, if we follow the default value, model.ONNX. And that will be the end of the script. Important thing here is if here somewhere in a script there will be some error, we simply will not get this message. Now let's modify this code a little bit in order to highlight the steps. So I have this code modified ready. So first of all, very important thing is ResNet50 model. So here we say that we download the pre-trained model. So we begin download and download. Next, we convert pre-trained ResNet50 model into inference mode. This is this part. And then finally, we save the model in ONNX format. And then they got the final message. Now, let's discuss the second file. The script which is producing TorchScript deployable version of ResNet50 model. So the starter script is very similar. We have the same inputs here, but we have a new part. Here we explicitly have to define a device. Basically, device can be of two types. It can be CPU or a GPU, which in this case is called CUDA. So if the computer you are using has GPU and it's properly configured, then device should recognize that GPU. And then here we will print out the device name. However, if your computer doesn't have GPU, it should switch to CPU, and then it will print result of information about your CPU. Next, in line 9, we do the same checking as in the previous file, that this file is run in a standalone mode. So basically you just run it from the command line directly, not calling it from some other Python scripts. Lines 10, 11, and 12 are the same as in the previous script. So here we create the parser, add arguments to the parser, and instantiate the parser. Line 14 is also the same. We download the pre-trained model, and we create a dynamic variable. And here we convert the ResNet50 into inference mode. However, line 17 provides a new piece of code which is allocating the model which is ready for inference onto the device. And this is necessary for next methods to be applied. So next we will use TorchScript method. So what this method is doing, it is basically scripting a function or a neural network model, inspect for the source code, and compile it as a TorchScript using the TorchScript compiler, and return a script module or a script function. In this case, we will have a script module, because the whole ResNet50 architecture is represented in terms of neural network modules. So we will have a script module. And here we will also have to save the model explicitly, calling the special method of the ResNet50 JIT object. And finally, if everything goes right without any errors, we should see this message with the default name of the model. In this case, the default name of the file will be model.pt, which stands for PyTorch. So now let us adopt this script as well. So here I'm adding additional printouts. So here we download the model. Here we convert the model into the inference mode. Here we detect the device, detect or define the device. The device to allocate model. And then we actually use this device to allocate the model in the inference mode. When I added just a few comments about what our torch.g.script method is doing, and here we're first converting the pretrained ResNet50 to TorchScript format, and then we save this model onto the disk. And then finally, if everything goes right, we should get this final message. So to run these scripts, I will use Nvidia PyTorch Docker container. So you can find information about PyTorch Docker container here in Nvidia NGC, Nvidia Cloud. So here is a detailed description of how container is organized, what are the layers, what are the tags, so what are the names of the different containers, and also important, here we can find information how to run the container. So I have already pulled this container. I can show you that I have PyTorch container already, and this is version 24.03. We will use this container in our experiment. And then here is the command which I will use to run the container. I will add one argument, -v, which will allow to mount the external device for the container. By default, you cannot save any information inside the container, and once you stop the container, all the results that you have computed inside the container will be lost. So we need the deployable versions of ResNet50 model to be used outside the container. Therefore, we will save those files into external mount storage, which in my case will be in C drive PyTorch directory ResNet50. And then I also apply GPU all, and the container version will be 24.03. So let's run the container. So let's run the container. Now we are inside the container, and I will create the files, PyScript files, inside, and I will show you that they are saved and the drive is indeed mounted. So currently the mounted drive is empty. We don't have anything here. So let me save this file. As ONNX underscore exporter .py, and this file is pt underscore exporter .py. Let's use Python here. Python file. So now we have two files in our directory. So let's see if we can see these files inside the container as well. And here we go. Now we have both files. So now, just to make sure that I can operate these files in the Linux environment of the container, we will give all possible permissions to these files. Now, Nvidia PyTorch container comes pre-installed with PyTorch and various libraries, and also there is one more important library we will use later, which is called TensorRT. This is Nvidia proprietary optimization tool, which is literally squeezing PyTorch and TensorFlow models into very lightweighted and minimal needed models, but we will talk about the TensorRT later. Right now, let's concentrate on the creating deployable version of ResNet50. So Python is already pre-installed, so let's run ONNX exporter file from command. And now we start downloading the pre-trained ResNet model from the PyTorch repository. This is completed. The model is optimized for inference, and then the model is converted and saved into an ONNX format. And finally, we have this file. Let's confirm this. And indeed, we have model ONNX file here. Now let us convert pre-trained ResNet50 model into TorchScript module. So we are using a CUDA device here. On this computer, I'm using GPU, and we can confirm the GPU status using Nvidia SMI command. So in my case, this is Nvidia GeForce RTX 3070. So that's why we have CUDA device here. Then we download the ResNet50 again from the repository, but since we did it already on the previous step, it doesn't take that much time. Then we convert the pre-trained model for inference. Then we allocate the model on CPU or GPU. In this case, this is GPU. And then we convert pre-trained model in a TorchScript and save TorchScript module. And here is my TorchScript file called model.pt. So let's confirm this. So now we have both models ONNX and TorchScript deployable versions, and you can see that the size of these models is very similar. and it's about something like 100 megabytes. Now, let us investigate one more way to create a deployable model using the TensorRT, which is optimization tools for PyTorch and TensorFlow models. I will explain the details of TensorRT in a separate video. And in this video, I will just use advantage of TensorRT being installed already in the Nvidia PyTorch container, and I will show how to convert ONNX model into the TensorRT model. So here I will use advantage of TensorRT being installed already inside Nvidia PyTorch container. So here I will show how to generate TensorRT model from ONNX model. Now let's go back again to the repository, and we will check our generate models file. So what we have done manually, this bash script is doing in an automated manner. So we're just calling ONNX exporter.py and pt exporter.py. So we have done it already. So now we will copy this command and we call it from the console. But before that, let us actually study what this command is doing. So first of all, we provide the model format, which is in our case is ONNX model. We take ONNX model as an input. Then the save engine, this will be our output model, model.plan. So this will be our TensorRT deployable file. Then there is explicit batch, which we show the batches explicitly. And here we provide the minimal size of the batch, which is 1. And 3 by 224 by 224 is basically a predefined size of the image. It will have 3 channels, red, green, blue, and the dimensions of the single channel will be 224 by 224. Then we provide the optimal size of the batches. This will be 128 images in the batch, and the maximum size of the batch is also will be 128. Then we provide a precision with which model should operate. So in this case, we select FP16, which is a half precision. This is basically 4-byte precision, comparing to 8-byte of full precision. And then we want model to print everything it's doing and then copy everything into the log as conversion.txt. So having this understanding, let's run TensorRT command in our container here. And it will take some time. So it takes essential time to optimize the model. So I will jump in the video to the moment then the model is generated successfully. So TensorRT optimization has been done successfully. We can see that the command passed, and now we should be able to see our model.plan file in the directory. So we have model plan and the log saved into conversion.txt. Now let's pay attention to one thing. While ONNX model and PyTorchScript model are very similar in size, they are around 100 megabytes each, the TensorRT model is nearly twice smaller. So I will talk about optimization techniques behind the TensorRT in the separate video. So now we can close the container and we can confirm that we do have indeed all these files generated in the container in our folder. And yes, we have all the files. We have the Python script files and pre-generated models and the conversion log. So that's it. In the next videos, I will show how to deploy ONNX, plan, and PyTorch script models on AWS Sagemaker using Triton Charter. So stay tuned for the next video. Thank you.